you can reach me on this email here. And I will talk about one of the homework problems, homework B, and that's about playing a simplified version of Tetris using reinforcement learning. And I will also give an introduction to Q-learning and a similar approach using neural networks that is called deep Q networks. So now I should be able to record. Okay. So let's start from the beginning. What is reinforcement learning? So reinforcement learning is inspired by how small children learn, that is by trial and error. So you interact with the environment and try different random things. So a small child tastes everything, and sometimes it tastes good and then it gets a positive sensation, and sometimes it tastes bad and then it gets a negative sensation, or sometimes they try something out and get hurt and it gets a negative sensation, and sometimes they do something and then get some food from their parents, which gives them a positive sensation. So by trial and error, they learn the behavior to behave in a good way as to get much positive sensation. And a similar idea is used in reinforcement learning. So the framework one usually considers is given by an interaction between something called an agent and something called an environment. And the agent is some entity that can take actions that somehow affect the environment. So the agent doesn't just take blind actions, so they take actions that are determined by something the agent can sense. So that's called a state. So provided a sensation of the agent, the state, it takes an action, and then it interacts with the environment for a while. And the outcome of this interaction is a new state and a reward that is given to the agent. So after interaction with the environment, the agent finds himself in a new state and obtains a reward that somehow quantifies how well this action work with the environment, so how the outcome of this interaction with the environment. And this reward the agent use to build up some experience. So the next time it will take an action, so it's in a new state, it will take an action and interact with the environment, and then it will repeat this loop by trial and error, and eventually it will build up experience to learn or associate the best actions given a state that maximize some long-term future reward. That is, it gets as much possible reward as possible in the long term. And this is a general framework, and it's used in many problems. And some examples are given down here. So it's used for gaming strategies, control theory, industrial optimizations, understanding nature, language processing, and other applications. So everywhere where you need to make a decision based on some information, you can use reinforcement learning. So I will, in the next slides, give some more detailed examples of what these states and actions and agents are. So now it's quite vague, but all examples will fit in this framework. And I just want to mention also that the learning uses a reward signal only, so you don't have any supervisor that tells the agent what is good and what is bad. So the agent learns itself by interacting with the environment. So you don't need to have pre-labeled data to train against. You have something, an algorithm that can learn just by measuring the response of the environment from taking different actions. So one example I mentioned was gaming strategies, and a famous illustration of this was done by Mihi et al. In 2015. And they use reinforcement learning to learn to play a game called Breakout, a computer game. And before training, they used a very simple random strategy that turned out to be just to move the paddle to the right. So the aim of this game is to move the paddle to bounce the ball to remove as many of these walls as possible. So before training, the agent doesn't know anything and just tries something random and move to the right, and it's not particularly successful. Probably it's just as bad as just moving it around completely randomly. But then after training for a while, it becomes better and learns to stay alive for a while, and by bouncing back this wall and by training even further, it becomes better and better, and eventually it learns to complete the entire area, and it finds these tunnels that are needed to complete or destroy many walls at one go. And in this case, the agent that does the actions is the player. So if a human were to play this, then it's a human that's the agent, but now it's a computer that gives input. So the artificial player is the agent, and the environment is given by the game. And also we can include the agent in the environment. So in general, we can define the environment as what agent interacts with, but also including the agent. So for instance, the states could also be states of the agent. So it's not only states of the environment. So for this example, the states used are the last 4 game images. So one could imagine having a single game image as a state, but if you just have a single image, you wouldn't know where this ball was moving, so you wouldn't know the direction or velocity of the ball. So it's not enough just to have a single snapshot to be able to learn, but by including several snapshots, the agent can learn how to play these games. And the actions in this example is that the agent can move in different directions. So it could either stand still or move to the left or to the right. So the actions the agent can take is different directions, left or right, with the joystick to move the paddle left and right. And then the reward is the game score. So if you get higher score, you get a higher reward. And that's what you want to optimize with this reinforcement learning process. And what's remarkable with this study is that they used exactly the same setup for playing 50 different games. So they used the same state for game images and same reward, that is a game score. And then they trained on 50 games and compared with a human player that had trained on the same game, and they were as good as or better than the human player in 75% of the games. So using the same setup, they managed to solve a general class of different game problems. And the algorithm they used in this study is also the algorithm you will use, or one of the algorithms, the deep Q network method that you will use for solving the Tetris game. but that will be somewhat simpler. So I will discuss that in more detail later. So now another example, also quite famous, probably you heard about this, is the Go problem. So for a long time, Go was the last game or a classical board game where humans still were better than computers. So backgammon and chess and such games, the computers are, there were already computer programs that were way better than humans, but until 2016, the best human player still was better than the best computer player. And the problem with this game is that there are a very large number of different states, and also it's hard to define what a good state is. So it was believed that it would take very long before computer algorithms could surpass humans, but using reinforcement learning in combination with some tree searches to define good states, the researchers at Google managed to beat the world champion in Go. And in this case, the agent is two agents. You have two different players that competed against each other during the learning. So they could have different strategies or the same strategy and play against each other. And by doing this, they will evolve and get better and better strategies. So initially, in 2016, with AlphaGo, they used a large database of human moves to build up strategies or refine strategies using self-play, where the agents play against each other. And then in 2017, they made an even better player from the scratch, where no human input was contributed. So only by reinforcement learning, the algorithm produced strategies that were better than the one that already beat the human in 2016. So the environment, as before or in the last example, is the game, and the state is the position of game markers. So it's a quite large game board, so there can be very many states. And the actions is to take a marker and place it on the game board on certain allowed locations. And the reward you use is typically a plus reward if you win and a negative if you lose. Another example is helicopter aerobatics. So there were supposed to be a video showing, but somehow the videos or all animations play automatically, so there's some problem. But anyway, you can look at this study and look up the YouTube video, and you will see a helicopter making different stunt moves that are quite spectacular and quite hard to do. So you need to be a real expert in driving to be able to do these different moves. And in this case, the agent is the helicopter operator, that is the controller that sends a signal to the helicopter. And the environment is the helicopter and the close surroundings. So basically, it's mainly affected by the wind conditions and, of course, the ground, so it doesn't want to crash. And the states are given by the physical state of the helicopter, the position orientation, velocity, and angular velocity. And the pilot or driver can change the main rotor tilt to move the helicopter either forward and backward or in sideways. It can change the angle of the main rotor, the attack angle of the main rotor, to make it go up or down, as you get with the same rotation speed, you get the larger or smaller intersection, cross section with the air, and it can change the tail rotor speed to make it rotate around its main axis. But unfortunately, we can't see this now because my animations were messed up. Okay. Another example, also in control theory, is self-driving cars. So it has been a big hype, but still we don't have them, or well, not completely autonomous cars at least. And in this case, the agent would be the driver. Environment is the car and the surroundings. And the states are the physical state of the car, but also a scene representation. That is, you somehow have different measurement devices that give you some information about your surroundings. And done by taking the actions of steering, accelerating, and braking, you want to achieve some goal, which would be to follow the road to get to some target and crash as little as possible on the way. Another famous example is used by Google. So they use reinforcement learning to find algorithms to cool their servers to reduce the power consumption for cooling. So they use it to reduce the power consumption. They don't use it to cool the servers. And in this case, that agent is the controller of the cooling system. The environment is the data center. States are the workload of the computers and the ambient temperature, the surrounding temperature. So if you have a high workload, you need to adjust the system to increase the cooling, and when you have a low workload, you can reduce the cooling, and by doing this in a smart way, you can spend less energy by not cooling when you don't need it. And they claim to save about 40% of the energy consumption for cooling in this way. So you control the cooling system, and the reward is well, that you don't have any power usage, and that the outlet temperature is within a certain range. So maybe they don't want to it to be too hot, because that could be painful for animals or humans walking by, or I don't know exactly what the reason is for this, or it could cause fires if it's very hot. Okay. And then a final example, which is related to what I'm doing, is understanding nature. So by using reinforcement learning, one can try to develop efficient strategies of swimming. So here is one example where some realistic swimmers interact with the fluid, and then a leading swimmer will create a wake in which trailing swimmers can adapt in a way such that the trailing swimmers can reduce their energy consumption. And then you can have several or different structures. And in this way, this is beneficial because these trailing swimmers will spend less energy. So this is something one could perhaps observe in nature and in schools of fishes, or also for birds in formation. You often see behavior where you have some leader, and then the trailing individuals save energy from swimming or behaving in a good way. Another example is a small micro swimmer that need to navigate some complex flow. And in this example, it's vortex flow. So before training, it will just move around randomly. But then by training, it will learn to move in a certain direction robustly. So in this case, the agent is the swimmer. The environment is some turbulent flow or a background flow in which the swimmer swims. And by measuring the flow properties, the state, and it takes different actions. That is the swimming behavior, and the reward is could be either to spend as little energy as possible, swimming in a target direction, or perhaps some combination of these, or in nature, probably the main target or reward would be to avoid being eaten by predators. So there are in nature many different competing goals, and by trying to reproduce behavior observed in swimmers by reinforcement learning, one can try to understand what different rewards, what different goals corresponds to different strategies that could be beneficial for the swimmer. And then, of course, in the future, it may be possible to create artificial swimmers, and then it's good to know what are interesting or relevant strategies for these to navigate in the flow. So that was some introduction of different examples, and many of them are famous, so probably you have heard of several of them before. And what you will do is a home problem where you learn to play Tetris. So I will try to start a program so you can see what it should look like. So now you should see a game board with a big square, with a 4x4 square. So this is one tile, and the lower 4x4 grid is the game board. And then the objective is to put these tiles on the game board. So you can put down a tile like this. So then it occupies a 4x4 grid on the game board. So you just drop it down, so it moves until it encounters an occupied site. And then you can rotate the tiles before you place them. So if you do like this, then you get to a state where you can't place the next tile. So when you try to place the next tile, you get a game over. So the aim of the goal is to not get a game over. So you want to be able to place the tiles. And to be able to do this, you can place your tiles such that you complete rows. So when I drop this tile here, it will complete the row, and that row is removed, and everything on top will fall down. So by completing rows like this, one can try to remove the rows, but still one can get in tricky situations. And the reward, so when I removed a row, I got the reward by 3. And now I am in a situation where I can remove 2 rows at one go. And then I get a larger reward by 10. So I will discuss this in more detail later. So you get rewards by removing lines, and then you get the game over if you place it in a, so you get an overflow of the game board. So it's a very simple game. So this is the miniature version, and then one can have larger grids and also the classic Tetris tiles. But to begin with, for the learning, it's hard enough to, or I mean, then it's doable quite quickly to just consider this small system. And some advantages of having a game as a system where we try to implement the reinforcement learning systems is that, well, you can make it reasonably simple as in this game, and you can get the visual feedback of what is happening, so you can see how the agent plays, and it's possible to get the feeling of how good the agent is performing, because you can play yourself and see if you can do as well as the agent, or so you will know or get a better feeling of whether the agent is playing good or not. Okay, So that's the game that you will try to solve if you choose this home problem. So as has been said before, there are 4 home problems and you need to solve 3 of them. And this is just exactly what I said before. And there are 4 different tiles in this game. So you have a tile set of these 4 games, 4 tiles, and you get the reward for completing rows. And some information on how to get started. You can find files in the file directory homeworks, homework B, Kristian homework B reinforcement learning.pdf. So that contains instructions for the homework, and then there are 3 files, Python files in the same directory, and you can run these files as they are. So you just need to make sure that you have all required packages, for instance these 4, and then you can try to run the program, and if you use the original parameters, you will get the same setup as I showed you just now. So you play as a human, and then to solve the different tasks using reinforcement learning, you can set a human player, so that's a variable, to 0, and use a parameter called paramset to different values corresponding to each of the different tasks in this homework B .rl.pdf. And you do not need to program the game, so that's not the focus here. So you will program part of okay, so that was so it's not a gameboard class .py that you should finish. It's the agent class. Oops. So gameboard, the game you don't need to do, as you need to finish the agent class by implementing the state, actions, and rewards, and the different learning algorithms. So that's the focus of this home problem. But of course, you can also have a look at the other files if you want to, and at some point it could be beneficial to, so you need to communicate with the game, and then it would be beneficial to have some feeling of what the game class does. Okay, so
I have just a general question, if that's okay.
Yep.
So I was thinking, it seems like reinforcement learning will be pretty effective when you have like these examples, games like short games or games where you get quick feedback. But how does it work for a more, I'm thinking for Go, for example, or for something that's more like strategically complex, where a decision you make now have a impact far away in the future?
Yes, so that's a good question. So the point of the learning algorithms that we will discuss is that they do not optimize the reward. So what they optimize is the long-term reward, the sum of the future rewards. So that means that even for this simple game, it will not necessarily just optimize to get 1 row completion. It may optimize so you can get better reward in the future. So that's built in the reinforcement learning algorithms, and that's the use of them. And it turns out that you can get very complex strategies in this way. So you have the Go example, for instance, and also the more recent example where they use reinforcement learning to play StarCraft 2 at a professional level, and that's very complicated, and you really need to have a strategy to play that game. So I would say that I mean, from the look of it now, you just it looks like you just take the instantaneous reward and update, but that is not really the heart of the reinforcement learning. So the heart is that you update how you choose the actions in a way such that the long-term future reward is optimized, not the instantaneous one. And also you can modify the learning to set a time window of optimization. So not to infinity, because maybe you have a very or an ongoing task. So then if you optimize until infinity, maybe you will never complete anything and everything will just diverge. So then you need to have a time window in which you optimize. So did that answer your question?
Yes, it did. And I guess I will get more context later.
Yeah. Okay.
Can I have also another question? Sorry.
Yeah.
Just wondering what kind of reinforcement learning is not. I mean, by the way that you describe it, you can also feel that even grid search, we can think as a reinforcement learning, because you try to optimize variables and you always go and see what's the outcome of your machine learning. You get something, you go back, you have a loop. So what we cannot do as really say with reinforcement learning? What is not really reinforcement learning?
Yeah, so I think, I mean, you usually do this distinction between supervised and semi-supervised learning. So, and unsupervised. So reinforcement learning is maybe somewhere in between, so semi-supervised. So, I mean, it is a different scheme than having a labeled data and trying to categorize the data, for instance. So I think the point of reinforcement learning is that the crucial input to the system is the reward. And it evolved a strategy to optimize the reward, but I mean, I think there are ways to map neural networks so you accomplish the same thing as reinforcement learning. So there is some overlap, of course. But I mean, reinforcement learning, as I will address it, is just this. So we have this loop. So I mean, this is what I mean by reinforcement learning. So this framework, that is what I mean by reinforcement learning. But then, of course, you can have a neural network that perhaps achieves the same effect as this, but in a more convoluted way. So it's just a straightforward implementation of this loop that is reinforcement learning.
So what I mean is I understand. What I mean is, so in the grid search, so yes, the outcome is your accuracy, so or whatever that it's the rewards also you're trying to accomplish. So then the agent it could be that the algorithm is trying to optimize and get what is the best values of the hyperparameters. So it can't we cast that thing like the reinforcement learning?
Yeah, so it sounds like a reinforcement learning problem, yes. So probably you can solve it using reinforcement learning, sure.
So what is so then if we can cast everything like reinforcement learning, what is the benefit of research compared if I do it with reinforcement learning? There is also Bayesian way to hyperparameter. I'm just trying to understand there are many ways,
yes,
and I'm trying to understand what reinforcement learning is not and what it is.
Yes, so I'm not so familiar with grid search. So I mean, perhaps you just want to optimize the instantaneous reward, or is it also a future reward?
It takes, I mean, the parameters of a space and trying to see what is the out of that space parameter space, what gives you the best final. So trying to find the best optimal value for example, let's say accuracy of your model. So yes, it iterates through many spaces randomly. It could be random choosing, or could be different kind of better strategies. Maybe reinforcement learning is trying to find the best way to move inside the space.
So reinforcement learning is a way to find the optimal strategy. I mean, you start at some usually a random strategy, but the long term or the aim of the network or the learning algorithm is to find the optimal strategy or policy. Of course, this is not possible in most cases, but you will find a local optimal solution. But I think probably it's just two different algorithms that solves the same problem. So from your description, it sounds like you could use the reinforcement learning also to solve the grid search problem.
Thanks.
Okay. So are there more questions? Okay, let's continue. So now to discuss a little. So I was thinking about doing group discussions, but maybe that's not so convenient. So maybe you could just take a few minutes, a couple of minutes yourself, and think about for our game now what. So the agent will be the player, the environment is the game and possibly the player, and the reward is we get a plus reward for completing rows, and we get a large penalty for game over. And also we have a finite set of tiles, so we have a maximum of 50 tiles in our game. So if we run out of tiles, the game is over, but we don't get the penalty. So the aim of the game is to place all 50 tiles and get complete as many double rows as possible, because that gives a higher reward. So now to achieve this, what are reasonable states and actions? So perhaps we can think about that for 1 or 2 minutes, and then we can try to come to a conclusion what the good states and actions are. Okay, so you had some time to think. So if we start with the actions, do you have any suggestions of what are the possible or reasonable actions in this game?
Wouldn't that be choose which rotation you want to drop the tile in? Which orientation?
Yes, so the orientation of the tile will be important. So if you place this tile at this orientation, then we will get an overflow and game over. If we rotate it, so it looks like this, we will be able to place it on the game board. So the rotation and to move left and right. So someone said in the chat. So the actions are summarized here. So you will have different actions for different tiles. So for example, the 4x4 square only have 2 or 3 actions. So you can place it in 3 different locations, but due to symmetry, it doesn't matter if we rotate it or not. So we only have 3 possible actions for this 4x4 box or 2x2 box. While, for example, this column instead has 7 actions. So if it stands up, we can place it in 4 locations. If it lies down, we can place it in 3 locations. And then we can redo the same for the remaining tiles, and it turns out that this one has 4 different non-degenerate orientations, and it can be placed in 3 places, so that's 12 actions, and this one has 2 non-degenerate orientations, so it has 6 actions. So this assumes that we have solid walls on the side. So in principle, you could also have a periodic boundary, and then you could place also these over the boundary, so to say. So then we would have more actions. But if we assume that we have walls on each side, these are the actions for the different tiles. So I hope that is clear. And then what about the states? What are good states for this game?
I would say it's like the drop tiles as a binary matrix plus our piece that we got to drop, like the position of it.
Yes. So the position of the tile, is that the state?
I would say it's part of the state because it's also like important where our, well, like the already dropped tiles are.
Yes. Yeah. So one way to represent the state is to use a tile identifier that is, we label the different tiles, and that's one part of the state. And then, as you said, we can have some binary representation representing the occupied positions of the game board. So we can represent this as some matrix. So -1 is unoccupied, and then +1 is occupied. But so that is one possible candidate for the state. But the position of this tile, I mean, we don't need to include that in the state because the position we determine by the action. So only label them so we know which tile type there is, but we don't need to consider which orientation it is because that is decided by the action later. So for the state, that is what the agent takes as input to make the action. So the agent doesn't need to know the orientation of the input because he can orient it himself. So if he just assume he knows it's one of the tiles, the agent decides which orientation to use. So this is the representation of the state that you should use in the program, but there are also additional information that one could use, or other representations of the states. So for example, one could use the height of the columns as a state. So here we have 3, 2, 4, 3. That would be one way to represent the state, or the number of holes in each column. So 0, 1, 0, 2, and so on. So one can have many different state representations. But if we have a binary matrix, all of these information is included. So having columns or number of holes, that is a way to reduce the size of the state, which would be beneficial for Q-learning, for instance, which doesn't perform well if you have many different states. But for the neural network, the deep Q network method, then perhaps it's better to have the entire matrix representation, because then you don't have any preconception. I mean, the states I mentioned, the height of the columns, so these are something that I think up. So that's a preconception of what a good solution is, that what I believe is essential information for the solution. So that you need to do in the Q-learning, where you cannot have a large state, but for the deep Q network, as we will discuss later, you can have a large state, and then instead the network decides what's relevant information to find the reward. So depending on which algorithm you use, it could be better or worse to have a different representation of the state. And other aspects could be if you, for example, know the future tiles, that could also be information in the state. So if you, for instance, are a computer in most games, or a computer AI, they also always seem to have more information than the player. So somehow you don't need to write as good AI if for the computer player if you allow it to cheat. And in this case, knowing future tiles would make it easier to make a decision and would make the gameplay easier. Another question is previous tiles relevant? Should you use previous tile types as the state?
That doesn't seem relevant, I don't think.
Yeah, so at least not if the tile sequence is stochastic, so you just get random tiles, then the previous tile is not relevant. So yeah, exactly. So someone suggested that. But if the tile sequence was deterministic, or there was some correlation in the tile sequence, then it could be useful to know the previous tile, because then you get additional information of what the coming tiles will be, or where in the deterministic tile sequence you are. And also, for that case, if you have a deterministic tile sequence, also the time could, or a number of the tile could be relevant information for the state. But for the problem you will consider, you should consider this representation, that you have the binary representation of the grid and the tile to be placed. And then finally, I will make just a comment on the reward, and then we will have the break. So the reward is -100 for a game over via overflow, and +1 for completing line, and +10 for completing 2 lines. So does this matter to have a +10 here? If we would just have a +2 for completing 2 lines, what would be the difference?
Then it wouldn't matter if you completed them at the same time or not, because it would be the same score per line.
Yeah, exactly. So if we just had a +2 here, then it's likely that a strategy found by the reinforcement learning algorithm is simply to just sweep up the lines as soon as possible. So as soon as there is an opening, you just place a tile and remove a line. While if you have +10, then it's more beneficial to remove 2 lines in one go. And that means that you need to build up some structure on the game board to make it more likely to be able to remove 2 lines. But it's, at the same time, you don't want to build up too much structure, because then it's hard to place the tile. So then it's becomes some kind of a trade-off problem where you need to build up structure while keeping it small enough to minimize the risk of having an overflow. So that's a more interesting problem compared to just removing lines as soon as you can. So this illustrates that the reward is very important for defining which problem you solve. So by just changing the reward here, we solve a different problem compared to having the reward +2. So the reward determines which is the task we solve. So for most reinforcement learning problems, this is very important to really think through what the reward is. So defining a good reward could be the difference between success and failure in having reinforcement learning solving some task. Okay. So I think we should have a 50 minutes break, and then we will continue at 9:05.
Now I can ask my question then. So from the things that I've learned, kind of from the things that you present, it seems to me that you, in the reinforcement learning, you need to know the full action, the whole action. You need to know the rules to play, and also that you need to know the complete, let's say, space somehow. I mean,
yeah, no. So I mean, the environment knows the rules. So that's just something that's done in simulations, or I mean, it could be the real world. So the reinforcement learning algorithm doesn't know the rules. It knows what rewards it gets from the environment by performing actions.
Well, yeah, but so the environment, let's go to the environment. So in the environment, you need to know the environment. For example, if it's talking about, if you don't know the bound, you are some person, you don't know the boundaries of the place, you just go there and you just find out, okay, so if I just walk to the wall, I get, I cannot pass the wall, but I don't know what's the size of the space is. So I just start to walk and explore a place. But for example, in this Tetris game that we are playing, we know the size of the space.
Yes, I mean, so I mean, if you didn't know the size of the space, you would try to make actions that are not allowed. So maybe you try to place the tile out here, outside of the game board, and then the environment should respond by giving you a penalty, because that's not an allowed action.
Okay, so we don't need to know there's space, the fullest.
Well, in principle, not, but for a representation in the memory, you can't have an infinite number of actions. Well, so you can do it with neural networks, maybe. Then you can learn without any prior knowledge. Otherwise, you would have a large number of actions that are invalid, but a finite set of actions.
Yeah. Can we also use reinforcement learning? So with this, because what I'm trying to say, how we can minimize a function? Can we minimization of a function? Because you said the optimization, industrial optimization is another way to use reinforcement learning. But can we cast a minimization problem, normalization? So you want to just minimize a function within its input parameters. Can we use reinforcement learning to find the optimal solution?
Yes. So I mean, the action would be to change the value of the parameters, I guess, and and then you get some function value that's the reward, and you just minimize. So that's straightforward. But maybe it's not the most optimal way to do it, but it should be possible to minimize using reinforcement learning.
Because I'm trying to, at that time, find out what is the reward, because you don't know where is the minimum of the function is. So you have to provide a lot of similar type of functions.
No, but if you evaluate the function, then the reward is just minus the value of the function. So then to optimize the reward, that's the minimum of this. So that's the maximum of the minimum of the function. And that's well, that's the minimum of the function.
Okay. The only thing is that we don't know how much kind of will be possible to go minus or plus, whatever. So
yeah, but that doesn't matter. So I mean, in this game, we don't know what the maximal reward is. So by playing it, maybe you can get 200 plus by removing 20 double lines. But maybe it's just 150 or 100. I mean, we don't know what the maximal reward is here.
Yeah, but in each action, you know what the cost will be. So it's +1, +10.
Yeah, but for the function, you also know the cost. It's just minus the function.
Okay, so that's the way to go.
Yeah. Probably it's not the best way to do it, but it should be possible to do it.
Thanks.
So I think it's time to continue again, so I will turn on the recording. So before the break, we considered the state actions and rewards of different systems, and in particular, we discussed the possibilities for the game, and we discussed what you should do in your implementation. So it's also described in the homework problem, the PDF file. And what I will do now in the second part of the lecture is to discuss the algorithms that are used to find the optimal policy, we say. So the best strategy to find, to optimize the long-term reward. So going back to the reinforcement learning framework, starting at the state, we need to choose an action in some way, and that is done following the current strategy, which is called a policy in a reinforcement learning context. And then we interact with the environment, in our case, the game board, and get the reward depending on which location we place this tile, which action we take. And this is repeated until game over, where we have an overflow or a predefined number of moves. So this is called an episodic task, and that means that it has a finite duration always. And that is in contrast to continuous tasks, where we need to optimize the learning in a time window, while in an episodic task, we can just optimize the long-term reward as far as ahead in the future as possible. So for the continuous task, you just make a small modification to the algorithm, but I will not discuss that in this tutorial. And this episode gives a sequence of states and actions and rewards. So we start at some state, take an action, get the reward, get to a new state, take the action, reward, and so on over the entire sequence. Well, as I said, reinforcement learning maximizes the long-term reward. And if we consider what different policies there are, so that is how to choose the action given a state. So we define a policy as a probability distribution, which we call pi, to take an action given that we are in state S. And some examples of different policies could be to always choose the same action. So this is a deterministic policy, and we can write it as just delta A1. So if we always take the action A1, then the policy is just a Kronecker delta function if we have discrete actions. Otherwise, it would be a direct delta function if we have continuous actions. And that's the discrete example. The policy could also be stochastic. For example, if it shows a random, uniformly random action among all NA actions, then the policy to choose policy AI given state S is just 1 over the number of total number of actions. So just a uniform number independent of the state. So both of these are independent of the state and very simple. But there are nevertheless policies how we could choose the action given the state. And then, okay, so there was a question here. So it's about the Q table, if the rewards are always trained. So you mean that the entries in the Q table are static in some cases, or so maybe, yeah. So usually the entries are trained, but for for example, the terminal state should always have a Q that is 0. So I will show that in a minute. So when you take the next or the final action, you don't have a contribution from the next state that you don't encounter. But I can address that question when I discuss the Q learning later. So these are two examples of ways to construct a policy. And the third way, the way we are interested in, is to choose an action with the largest optimal value, we call it. And we denote the optimal value by a Q of the state and action. And this policy we note by star, pi star, is to take the action A star in a given state S, where A star is the action that has the largest Q value, the largest optimal value. And this Q function here is equal to an expectation value of the future rewards. So this Q function, if this is correctly described, this is just the expectation value of all future rewards. So if we choose the action that gives the largest expectation value of future rewards, that would be the best action, because all other actions would give lower expected future rewards. So if we choose have this policy, then we are sure to have the optimal solution. So this must be the best policy. So we always choose the action that gives us the largest expected future rewards. So on average, this must be the best policy. So the complication is only that we don't in general know this function Q, the expected future reward. So the goal of the reinforcement learning is to find this Q function. And if we have this Q function, we find the optimal policy by just always following the action with the largest Q value. Okay. So how can we find this Q function? So that's all about what reinforcement learning is all about. And one example would be to find the optimal policy by evaluating the Q function for all policies. So we evaluate Q, that is the expected future reward, with a subindex pi here. So that means following the policy we have selected, we evaluated expected future reward. And by doing this for all different policies, then the optimal one must be the one that has the maximal Q value for all different states. So the policy that gives the largest expected future reward, that must be the optimal policy, and that gives the optimal value, and that gives the optimal policy. So we just compare all different policies, evaluate the Q function, and choose the one that is larger than all others for all states, and that is our optimal policy. So it's not obvious that this condition exists, that you can find a function or a policy that such that Q is larger than the maximum of all other Qs for a general state, but it can be shown that if we have a Markov process, it is possible to find such a solution. So then we can find an optimal policy in this way. So this is a brute force method. So we just evaluate everything. It takes very long for each policy to evaluate the Q function. And since the number of policies grow very rapidly, so in each state you can take, say, NA actions. And if you have NS states, then there will be NA to the power NS actions. NA to the power NS different policies. and this scales very badly with the number of states and the number of actions. So only for very small state and action spaces, this would be feasible, but in principle, one can do it. And then there are different versions where one do some, not evaluating all policies, but some sampling of policies, some Monte Carlo methods that where you sample different subsamples of policies. So that's one way to try to solve the problem. And the second way is Q-learning. So now, and this is an algorithm to find the optimal policy, ideally, if you run the learning for long enough and have enough exploration. So from what we know from the previous slide, the optimal policy is given by the action that gives the largest Q value. And this optimal value is defined by the expected future reward. And this we can rewrite as the immediate expected future reward, the immediate expected reward plus the sum over following rewards. And since we follow the optimal policy, this means that after the current state, we will take an action according to the maximum of Q, and this action will have the value, the maximum of Q at the next state. So in the next state, we will just take the best action, the largest Q, and the corresponding value will be the maximal Q of all actions. So we can rewrite this sum over all reward for all future state in terms of the Q matrix of evaluated at the next state. So in this way, we can have a recursive relation, which is an identity if Q is the maximal value function. And this lies at the heart of reinforcement learning, because if we have a prediction of Q and we get a new reward, then we can look at the sum here and our current guess and see, look at the difference. And if this difference is 0, then we are happy. Then it seems like Q is a good approximation. If this difference is non-zero, then we think that we must adjust Q, taking this new information into account. So that's what we do in an algorithm called Q-learning. So in the Q-learning algorithm, we start with an arbitrary value Q, which we call Q0. So it could, for instance, just be zeros. So we assume it's just zeros to simplify. And the next step is to evaluate the initial state at t equal to 0. Then we choose an action. So we just follow this scheme. We choose an action according to the policy. And for instance, we could have the optimal policy, the greedy policy, if we believe this Q is a good estimate of the future reward. So we just take the maximum value of Q. And in this case, Q was just 0. So then we just take a random action of all the maximal ones. So there was a question. So aren't we assuming that immediate action has no impact on the future choices? Yes. So we assume that in Q-learning, we assume that the system is Markovian, which means that if we take an action provided a state, the transition probability just depends on the immediate state. It doesn't depend on earlier states. So that's an underlying assumption in Q-learning and also in deep Q networks. And in reality, perhaps this is not the case. So then we are not guaranteed to find the best solution. But usually the Q-learning still works to find a good solution, even though we are not guaranteed to find the best one. But even if we have the Markovian system, we would need to run the system for an infinite number of time to really ensure that we find the best solution. So there is still a problem, even if we have a Markovian system. And another note on the Markovianity is that in most cases, even if the system is not Markovian, we can make it Markovian by including more information about the state. So for example, if you remember the video game, if you just have the immediate video frame and try to learn, you can't really learn anything because you don't know how this ball is moving in the system. But if you include a history, so you include 4 video frames, then you have a larger state space and the system become more or less Markovian. So if you have a problem that the system is non-Markovian, we can make it Markovian by providing more information, assuming that it is possible to find more information. So in some cases, maybe you can't find more information, and then the system is maybe non-Markovian. And if it's bad enough, maybe you can't use Q-learning because of this. But that is something we assume that the system is Markovian, so things doesn't depend on the history. Okay. So we chose this action, and then we interact with the environment, and we get a new state and a reward. And at the same time, we use the reward to update our Q matrix or Q table. So initially, it is just blind, so we don't have any strategy initially. But then we update the Q table using the reward we have learned. So at the next time step, we use the old Q table plus alpha, which is some learning rate. You can assume it's 0.2 because that's what you will use in the home problem, times a delta Q. And this delta Q is just the difference between the right-hand side and the left-hand side here, if we neglect the average. So we form this delta Q as RT plus 1 plus the max Q. So this is provided this information, what we think the future reward will be, which is the immediate reward plus an approximation of the future reward that is approximated using the Q table. And then we form the difference to our current approximation of the Q table at the current state. So this is evaluated at the next state because this is what we expect will happen after the next state. So this is if we don't want to evaluate further into the future, this is our best guess of what the how large the difference between the actual Q value and our current guess is. So we use the new information in terms of the reward to update the Q table in this way. So I will make a couple of examples on the next slides. As I said, a terminal state. So if this ST plus 1 is terminal, that is, we will stop here and not take any other action. Then the Q must always be 0. So we don't expect to have any additional reward because we will not do anything more. So that Q is always 0. Otherwise, we don't have any, in general, we don't have any conditions on the Q. Perhaps it could be so that we can, by looking at the model, we can actually find out what the Qs are, and then of course we could hard code them. But that would be very problem specific. So that's related to the question earlier. So if we have, for instance, a deterministic system, and we know that if we do this, then this, and this will happen, and that will always happen, and we can estimate the Q value or the expected future reward because of this, and then it makes sense to have a hard-coded Q value, but otherwise we use the Q learning to update the Q table.
Can I ask you a question about, I think it's related to that maybe.
Yeah.
So here we have Q depends on T, but wouldn't we want the Q values of a given state and a given action always to be the same, regardless of when in the game they occur?
Yes. So the point is that we need to, I mean, the final policy that you use to play the game, that will be independent of time. But this is a process to find the final policy. So initially, we don't know anything. So we just perform randomly. So that's not a good policy. So that we don't want to keep. So we update Q until it converges to some values. And when it has converged, then we use this Q matrix to play the game in reality. So this is a training sequence. And then when you have converged to an optimal policy or something that's close to optimal, then we use that for playing the game. And then, of course, we don't change the policy anymore. So then we just stick to the final policy. Okay. So that's the update. So that's one way, one loop in this framework. And then when we get here, we have a new state, which is fed to the agent. And then we can choose a new action. So we repeat from step 3 and move over and over. And we continue doing this until the episode is finished. And so until game over or the tiles run out. And after that, we make a new episode starting from state 2. So we restart the game, start with the initial state, and repeat everything. But now we keep the learned Q matrix. So here we will start with the Q matrix from the end here. And then by repeating over many episodes, that is many games, we will get a better and better Q matrix ideally. And in the end, depending on the algorithm, the Q matrix would converge to some definite strategy, which is a close to optimal one, ideally. Okay, so this is the Q learning, which is the classical way to do, or one common method to do reinforcement learning. So was there any question? So there's a question about if you run the whole algorithm multiple times, is it possible to convert to different Q tables? And the answer is yes. So ideally, you will converge to the best one, but that is provided that you have enough exploration in the scheme. So in this current case, we don't have any exploration, and we will therefore converge to a certain, we will converge to a certain Q table, but not the optimal one. And then one needs to add exploration to be able to find the global optimum. So that it's always tricky with learning algorithms to ensure that you find a global optimum rather than a local one. So I will just illustrate. Okay, so now everything is shown at once, so that's not so good, but just how this update goes. So starting from a state as hat, so this is our initial state. We shows an initial empty Q matrix, so all entries are 0. And on the tie, we should choose a random action. And for example, we randomly find that the chosen action is A1, and we place the tile at this position. And this means that we will have an overflow and a game over and reward of -100. And updating the Q table using our delta Q multiplied by alpha, we find that so this is a terminal state, so this must be 0. And initially we don't know anything, so this is 0. So we just get the reward as delta Q, and then we multiply this by the learning rate alpha and get -20. So the next time the same state is encountered, we have learned that this is a bad move and it has a negative value. So we just have a selection between the other two moves to place it at the second or third position, and then we choose one at random again. And in this case, it chooses the third position, and then it completes 2 lines, get the reward, and we update the Q matrix in a similar way as up here, and we get an entry that's 2. So the third time this state as hat is encountered, then we get we have a Q matrix that has learned that this is a good state, so it will show the action A3 again.
I'm sorry, maybe I misread the algorithm on the previous page, but doesn't this require that this happens on the exact same time t for the QT to have these entries?
So, I mean, this is just an update. So Q will change with time. So that's all that this T index indicates.
Okay, so we actually replace the entire matrix for that state in action.
Yeah, exactly. So here is Q0, here is Q at time T. So always refer to Q at time T. So it's just to give a notation that Q changes with time. So the matrix changes with time, and that's the case here. So here it's 0, 0, 0. Here is a different Q matrix that has changed with time.
Okay, the matrix changes with time, but we always use the latest one.
Yes. So I mean,
okay, that makes a lot.
Yeah, okay,
more
sorry
sense.
for not being clear about that. So all other ones are, so this is just a replacement of the Q matrix. You replace one entry in the, okay, Q table, I should say, because it's not really a matrix, but in the Q table. So it's not, I mean, you don't need to occupy a new memory or anything. You just have the same Q matrix and change one entry in this Q matrix or Q table.
Thank you.
Okay, so that's one example. Another example is if you have another state as double hat, and initially you choose an action randomly, and you choose the left action here, and we complete one line, so we get the reward R equal to 1, and the Q matrix is updated. So now the first entry here is the maximal one, and with the algorithm on the previous page, we will always choose action A10, but we haven't tested the other two. So I mean, this looks good, so we will always get a reward by doing this move, but this is just a short-sighted approach. So we just optimize the short-sighted future reward in this way, because actually in the long run it would be better to place the 2x2 block on this position, so you fill out this part of the game board, because this is a very good state, because if the next tile is a 2x2 block or this angle block, we can complete 2 lines, or if it's the column or the diagonal block, you can complete 1 column on the next tile, and you will also have a good position to complete even further lines on further tiles. So in fact, this is a much better state to be in for the future compared to what you get by completing a single line by placing the block here. So if we just shows the optimal action at all times, we will miss this structure or these possibilities. And the solution, so we can find also these strategies that initially seems suboptimal, is to add exploration. And with exploration, we mean that we shows actions that are not always the optimal one, but we can try some other actions occasionally and see what happens. And an example of a policy with exploration is an epsilon greedy policy. So in this case, we chose the action as either a random action with probability epsilon, or the optimal one, or the current estimate or the optimal one otherwise. So this will add some exploration, and usually we choose epsilon to be quite small, so we don't explore all the time, because then we will just have a random strategy, but we do it occasionally, and then we can find this other configuration. And since what will happen after this configuration will give a large reward, that means that the Q value of the next state will grow, which means that eventually this state will become large, even if you don't have an instantaneous reward, because the following Q value becomes larger and larger because you will complete rows in the next state. So in this way, we use information from the future, backpropagates by updating the Q tables, and we obtain this information when we choose this state, and eventually this will give a larger Q value than this 0.2, and we will always choose this action to put it in A3, even if we just look at the instantaneous reward, it is the best to put it in the left. So this is basically the mechanism in which we get a strategy that optimizes the long-term reward. So we use rewards further ahead in the future to update the Q table, and then we use, when we update Q tables earlier in the history, we use future Q tables as part of the input and also the immediate reward, and this builds up so we get a good approximation of the value of future rewards. So there are some questions now, so let's see here. So it's a question about a random valid action still able to take the otherwise short-term optimal action. So that's so usually I think one include also the otherwise action, but that's just for simplicity of programming. So I think it doesn't really matter. So it just affects the value of epsilon. So if you have epsilon 0.01 and decide to have any action, then occasionally you will choose this one. But in principle, you can get exactly the same effect by choosing epsilon 0.012. So you have a little larger epsilon. No, a little smaller epsilon, I mean 0.08, for instance. Then you will choose this one a little more frequently and random of the other otherwise. So it's just a matter of making it a simpler implementation. It's just, you can adjust or get the same effect by just adjusting epsilon somewhat. So next question. So the Q table shown has 3 possible actions. Does it mean that each tile has an associated Q table? Yes, so that's one way to set up. The other way is just to have a large Q table with, say, the maximum number of actions, which is 12 for the corner tile times the number of states. And then you will never encounter many of the entries in the Q table, so you just gather everything in one place. And another way would be to make a more memory efficient way representation. So you just have one Q table for the 2x2 block, and one for the corner block, and one for the column. And they will be equivalent. But I think the easiest is to just have a large Q table with all states and all actions, and then you will never encounter most of them. And then if you encounter memory problems, you can fine tune this, but it's just a matter of choice how you do it. It's just a question of if you want to keep entries that you will never explore in the Q matrix. Okay. So, we're running short of time, so let's see if we can continue. So that was the Q learning, and then the equivalent for an alternative method using a neural network is called deep Q networks. And basically, we use the same scheme as in the Q learning, but we replace the Q table by a deep neural network that we call QNN, or I call it QNN, and is can be viewed as a function of SNA. So in the Q table, you have given a state, you look at the corresponding row in the Q table or column in the Q table, and look at the entries corresponding to each action. So that's just a list of the Q values. Another way to get the same effect is to use a neural network as a lookup. So we start with an input state that is the binary grid and tile identifier, and then this network gives an output. So this should be equal to the number of nodes here should be equal to the number of actions, or the maximal number of actions rather. And for each action, the output here will give a value. So the value of these outputs are correspond to the Q values. So numerical value correspond to Q for a given state S. So for any S, we will get some output numbers. So we get a Q of S, and the action is the different indices here. The different nodes give the value for each different action. So so instead of having a table where we look everything up, we have a neural network that takes an arbitrary state as an input and gives a mapping to the actions. So I will just mention that how I did with the tile identifier here. So this is the binary representation of the game board, and then we make some pre-processing. For example, in the Atari games, they use convolutional networks to analyze the images. Perhaps it could have been good to have some convolutional network to find structures in a Tetris game, particularly when this becomes large. But for the small case considered here, I found that not doing the convolution layer doesn't really affect so much. So I didn't see much gain in having a convolutional layer here. So for the first task 2A that you will encounter, it is enough to just don't do anything here. Just feed the data to the network as binary -1 and +1. And then I represented the tiles as input -1 if the tile is not the current tile, and +1 if it is the current tile. So for example, if the current tile is this corner tile, we have minus, minus, plus, minus. If it would have been the column, it would be plus, minus, minus, minus. So I just put the plus sign on the current tile. And this is the input. I put some dense neural networks, and the output is an approximation of the Q value. So we chose the action with an epsilon greedy choice as before. So we have some exploration, so it's random with probability epsilon. And in this case, we take the probability to depend on the episode number. So epsilon E is the maximal of epsilon, which is the final number, and 1 minus E naught. So E naught is some scale of episodes where we have a very large exploration. So initially epsilon is 1, so we start by just playing randomly, and then at the scale epsilon 0, when we have an episode that's larger than epsilon 0, then we just have the small epsilon, so then we have a more reasonable exploration. So we start with extremely large exploration and then decline it in this deep Q network algorithm. So that's the epsilon case, and then if we don't have the probability smaller than epsilon e, we just shows the action correspond to the largest output node here, similar to the largest Q value in the table before. So why do we do this? So the reason is that the Q table method is not very good if we have a large state space, or if the state space is continuous, because since we need to visit all states a large amount of time, it takes extremely long to converge. While if we have a neural network, we can hope that it can map similar states to the same output, so it can somehow identify patterns of similar states to make generalize what we learn for a certain state to close by states. So this is the main difference to the Q learning. So we will also have a couple of additional modifications. So the aim is to minimize this delta Q. So it's the same as for the Q learning. That is our current estimate of the future expected reward following the current Q matrix or Q network minus what we believed earlier. So this is what we believe with the new reward or the new information we get, and this is what we believed earlier. And we want this to be as small as possible so that we have a good approximation of what happens in the future. And we want to minimize this for all transitions or many transitions from one state to another. So these are these quadruplets that are generated by this reinforcement learning scheme we have looked at before. So we want to minimize the loss function where we sum over many transitions. And one problem is that data is not independent and identically distributed, which is something that is needed to do stochastic gradient descent. So this is because close by, or in one episode, one expects states to be quite correlated. So subsequent states are quite similar. And identically distributed is also not true because the Q network will change with time, because initially it's just random and then we learn, so they will not be identically distributed. And the solution to this problem is to build a buffer, called an experience replay buffer, containing a large number of last state transitions. So I think I suggested 10,000 in the home problem or something. So we have an experience buffer of many of these quadruplets, and among these we chose a smaller number, say small b equal 32, which forms a mini batch, and we use this mini batch to train the network at one given time step. So we use stochastic gradient descent to optimize the loss function for evaluated using only this mini batch to get an updated network. And a second problem is that we have bootstrapping. So that means that we use a QN to estimate the expected future reward when we update. So we have this expected future reward that follows the Q matrix or the Q network. this is good because I mean, this will speed up learning. So this is something we want. But the problem now when we have neural networks is that when we update the Q network, it may be so that we also update the Q network for similar states. So we could update it also for the next state, and then it is possible to have some runaway growth. So perhaps this is very large from the beginning, and or too large and overestimate from the beginning, and the Q becomes gets updated to a value that is an overestimate. But when you update the Q, you also update this one, so that this one becomes even larger, and then we can have some runaway growth. So to get away from this problem, we introduce something called a target network for estimating the future reward, so the maximal here. And this is essentially the same. It's a copy of the Q network, but we keep it constant for a long time, and then we update it only occasionally. So the Q hat we keep mainly constant, but then occasionally we copy the weights from the Q network to Q hat to update it. But we don't have the problem that the target network here is updated at the same time as the Q network. And then the algorithm is shown here. So it's essentially the same as the Q learning, but with these modifications. I will not go into the details because I'm running out of time. So I will just finalize by mentioning the different assignments. So as I said earlier, you should complete the classes for the Q learning and deep Q networks in the agentclass.py file. And then you should address some different questions. And the first question is to use regular Q learning to train a player of this game, the Tetris, simplified version of Tetris, on deterministic tile sequences with greedy policy. And the reason for this first choice is that this is something that can be done very quickly. So you can get convergence in a minute or so on the computer. So it's a good testing ground. And then you will build up more and more complicated scenarios. So in B, you use epsilon greedy policy. In C, you use a random tile sequence instead. And in D, it's a discussion question on what happens if you try to scale up the Q learning method to a larger game board. And then the second task is to solve the same problem with the random tile sequence using the deep Q networks method. And then optional is to solve the problem on a larger game board using deep Q networks. So this gives 10 points. So this is the task, and this is something special if you're really interested. So I didn't manage to get it to run or work for the larger game board, but maybe I didn't put down enough energy. So I expect that if you want to address this question, you would need to work quite hard, and the reward is just 2 points, but it's something if you manage to get to some reasonable conclusions. But this is just bonus if you are really interested in the subject. So, okay, so that's what I wanted to say. So there's a question